Hey guys, welcome back. All right, so the last chapter of the course, guys, is called Permutations, Combinations, and the Binomial Theorem. If you're in my class, we do this chapter first, and we actually do one more chapter at the end over there like that. So this is the last chapter in the textbook, kind of the second last chapter that we do, depending on whose class you're in like that. Throughout doing this course, this is probably going to be the last chapter that we do. So there's 11 chapters in our textbook, and that we kind of cover in Math 30. And I can say that 10 of those chapters are all what I call pre-calculus units. Okay, and so what I mean by that is like the study of functions and kind of the different properties of how they work, and this is leading towards your Math 31 course or your calculus courses that you'll take in university. Now, the 11th one, which is this one, is I'm not going to describe this as a calculus unit. This is more of a pre-statistics unit or a pre-probability unit. So what probability is a ratio of the number of successful outcomes over the number of possible outcomes. Okay. Now, if you say something like if you roll a dice, what's the probability of getting a 4? Okay, well that's gonna be just like 1 out of 6. That's pretty simple. Okay, so there's one successful outcome and then there's 6 possible outcomes. Now, if you start like just more complicated examples, like if you're playing poker, for example, and you have a 5-card hand, like what is the probability that you get a full house? Okay, a full house is like where you get 3 of the same card and then 2 of a different card. So you get like a 3 of a kind and a 2 of a kind. Okay. Well, I mean, that becomes a lot more difficult to how to do. So like how do you figure out how many possible full houses there are? And then how do you figure out how many possible total hands there are? Okay. So what this unit really can be recalled as, I'm going to say it's going to be called counting methods. Okay. Now, again, it seems very simple, but guys, in this unit, counting is going to get hard. Okay. So for counting methods, so we're counting methods like that. We're studying different ways of counting, like how many successful outcomes or how many possible outcomes. Now, we don't really study probability in this course like that. It's just kind of the counting methods that we use, and then you'll use these methods in your stats and probability courses down the road on kind of how to kind of figure out some of these problems over here. All right. So, first example. Is what we call the fundamental counting principle. Okay, so in this case, like how many digits are there in between 100 and 999 that do not contain the digits 2, 5, or 7? So in other words, they're saying only using one, 3, 4, 6, 9, or 0. Okay, so how do we actually do a question like this? Okay, now what I'm going to do over here is I'm going to do a very big, we'll call it tree diagram here. So what I'm going to say over here is like my first row, like I say, is my first digit. Now, if I need, so what I have here, in between 100 and 999, this is going to be a 3-digit number. Okay. Now, the thing about 3-digit numbers is a 3-digit number is not allowed to begin with 0. Okay, it can begin with 1, 3, 4, 6, or 9 in this case. Okay, but we can't begin a 0. Okay, so our first digit could be 1, 3, 4, 6, or 9. Okay, so it could be any of those guys over here. Now, our second digit, and this is where it's going to start getting big, and it's going to get really big after this. So let's suppose that my first digit was a 1. Okay. Now, what could my second digit possibly be? Well, there's going to be 6 possibilities. My 6 possibilities are It could be a 1 again. It could be a 3. It could be a 4. It could be a 6. It could be a 9. It could be a 0. That's another possibility there. Okay. Now, if my first digit was a 3, what would my possibility be? Well, it could be, again, the same numbers again. So it could be those guys over there. I'm just going to follow this pattern through. So it could be those guys as well. Okay, so let's kind of follow this possible tree over here. So the way I interpret this, if I'm listing my possible digits over here, like if I start with here, that means my first digit would be a 6, and if I go to here, as I go to here, my second digit would be a 4. Okay, so because I'm not going to have enough room to do everything for my third digit here. Okay, but the idea is for every one of these possibilities in my second digit, I'm going to have the same tree diagram going for 6 digits after. So it could be 1, 3, 4, 6, 9, 0. Okay, so again, it follows again. Suppose we go to 6 to 4, and then go to 3, right? So that would be like 643 is one of my digits between 100 and 999, and this digit does not contain 2, 5, 7, or 8. Okay, so again, like there's not enough room to be able to do all this. Okay, but the purpose of this exercise is not to list all the possible digits, because there's going to be a lot of them, but it's a question of saying how many digits are there going to be. Okay, now the way we can do this is really this question. We're making what we call 3 choices. Okay, now in the first choice, and I say the 3 choices are the choice for digit number 1, the choice for digit number 2, and the choice for digit number 3. So this is like digit 1, digit 2, and then digit 3. Okay, well, when we look over here, how many choices do we have for digit number 1? Well, we had 1, 2, 3, 4, 5 choices. Again, it wasn't allowed to be 0, because if we begin with 0, it's not going to be a 3-digit number. So we had 5 choices here. When I look at digit number 2, how many choices did I have there? So, okay, so for every one of these guys, for every one of these 5, well, there was 6 options here, 6 options here, 6 options here, and so forth like that. So my choices for digit number 2 is 6. Now, if I count here, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So far, 5 times 6 gives me 30 possibilities for just my first 2 digits. Okay, and then after that, I'm looking at my third digit. Okay, again, my third digit can be 1, 3, 4, 6, 9, or 0 as well. Okay, so that's going to mean we have 6 digits as well. So the answer over here is going to be 5 times 6 is 30, times 6 equals 180 different possibilities here. Okay, so what the fundamental counting principle deals with is we're dealing with problems where essentially you're making a series of choices. Okay, and you need to think, well, how many options do I have for choice 1? How many options for choice 2? How many options for choice 3, and so forth? And then you want to multiply those number of options together, and that's going to be your total number of cases that they'll have at the end. All right, so example 1. So this one, we actually are going to list, so we're going to roll 2 dice. Okay, so you're playing Monopoly with your brother or your sister at home. Okay, so if you have this, like, so the tree diagram would be, I'm going to say dice 1, and you have your dice 2. Okay, well, what are your possibilities here? Well, for dice 1, you could have a 1 or a 2 or a 3, or a 4, or a 5, or a 6. Okay. Now for your dice 2, suppose you roll your first roll was a 1. Well, then this is going to make another tree diagram like this, where it could be a 1, 2, 3, 4, 5, or 6. Here, 1, 2, 3, 4, 5, or 6. And then here, just put like an arrow, it could be 1, 2, 3, 4, 5, or 6. All right, so here are your potential rolls. Now the way I'm just going to do this, I'm going to kind of group these and write them as an ordered pair. Well, we could have 1, 1, 1, 2, 1, 3, 1, 4, Guys, the point I'm trying to get over here, listing the potential outcomes is a very cumbersome and a very long activity. We're not going to be doing this much in this unit here. Point is, I hope you're kind of realizing this as well, there's going to be a total of 36 different possibilities here. And so, and using the fundamental counting principle, the way we get that is there are 6 options for the first dice, and there are 6 options for the second one. So 6 times 6 is 36. Okay, and that's going to be the total number of outcomes that we'll have in a second here. Okay. Here's just this again, guys. What's one of the biggest outcomes of probability, or biggest applications? I'm going to say polling. You know, what's the probability that Donald Trump actually wins the state of Pennsylvania? Okay. You know, there's polling organizations are going to kind of be able to make predictions about that. Okay, so they're saying, okay, based on the data we have, we just see this, and if you watch the election this week, guys, like that, you know, it turned out the polls were definitely wrong, like that, right? But it's the polling is trying to predict who's going to win stuff in things like politics in there as well. Okay, you'll see probability in sporting events. Okay, so what's the probability that this team's going to win? What's the probability that this team's going to win? Okay, and really, why do we do that? It comes down to gambling. Okay, and in Vegas, like that, you know, in gambling, and probability in card games, and probability in dice games, it's how these games are really chose. Okay, so the question says, using this data, are you more likely to roll a 7 or an 8? Okay, and it also says what is the least likely rolls. Okay, well, if you look at this, what are my possibilities of rolling a 7? Okay, so I'm talking about like a sum of 7 here. Okay, well, if I want a 7, I could have like a 1 and a 6, a 2 and a 5, a 3 and a 4, a 4 and a 3. Okay, we have a 5 and a 2. We have a 6 and a 1. So there are 1, 2, 3, 4, 5, 6. So over here, guys, it's like the probability of a 7 is 6 out of 36. Okay, now which is simple same thing as 1 over 6. What is the probability of an 8? So probability of rolling an 8 is, well, where are my 8s going to be? Well, I could have, if I roll a 1, I can't get an 8. Okay, but it could be like a 2 and a 6. That would get me there. A 3 and a 5 would get me there. A 4 and a 4 would. a 5 and a 3 would, and a 6 and a 2. So it's going to be 1, 2, 3, 4, 5. Okay, so the probability of rolling an 8 is a 5 out of 36. Okay, so imagine you're at Las Vegas and you're staying at the Bellagio Hotel and you're playing a game. There's a game called craps. Okay, so this is kind of a dice game. And like, would you be more likely to throw a 7 or to throw an 8? Okay, well, based on probability, you are more likely to roll a 7. Okay, so rolling 2 dice, the highest probability you're going to get is actually going to be a 7. Okay, now what are the least likely rolls? Okay, I can say the two least likely rolls, a p of 2. The only way I can get a sum of 2 is with this guy over here. Has 1 of 36, and the probability of rolling a 12 is going to be this one over here. It's the only way I can roll a sum of 12. So that's going to be 1 out of 36 as well. Okay, so guys, I mean, this example over here, like, the purpose of the units is like, how do we count the number of outcomes? Okay, we're not going to be doing this every time, what we call a big tree diagram like this. Okay, it takes way too long, and like, we're going to be dealing with cases where there could be hundreds of thousands or millions or even billions of possible cases on some of these examples that we're going to be doing. Okay, so like, writing out tree diagrams is going to be impractical for those like that. Okay, but still good exercise. Again, why are we doing this? So we can start counting outcomes. Okay, and like, what are the possibilities for that? Okay, just over here, guys, like that. If you're playing like that, if you ever do find yourself in a casino, just be aware of stuff like this. Okay, this is your highest chance of getting this. Okay, the highest chance of going to roll 2 dice is going to be getting a 7, rolling a 2, which is called snake eyes, or rolling double 6s for a 12. These are going to be your 2 lowest probability rolls. Okay, so if you're putting bets down on something, your chances of winning are going to be higher for this and lower for this. Okay. Now, the other thing is the way that these games work. If you bet on this, you have a low probability. But if this outcome happens, your payout is probably going to be much, much higher. Okay. So since this is a higher probability event, your payout is going to be lower if you win by betting on this. It's going to be a higher payout, but a lower probability of getting these guys over here. Okay, so example 2 says, how many multiples of 5 are there from 10 to 95? Now, what I'm going to put in brackets here, I should have said the word inclusive. What that means, that I'm going to include the number 10 and I'm going to include the number 95. Okay, all right, so if I'm going to be including these guys over here, the idea is, well, okay, so let's list them out. What are all the multiples of 5? Well, we have 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, 75, 80, 85, 90, 95. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. There's 18 different possibilities from 10 to 95. Now, using the fundamental counting principle, we're really making a 2-digit number. Okay, so this is digit 1, and this is digit 2. Now, what are my options for digit number 1? Okay, well, my options are is 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9. Point of this is there are 9 different possibilities for digit number 1. Okay, what could digit number 2 be? Well, since it's a multiple of 5, digit number 2 could be a 0 or 5. That means there's 2 options there. 9 times 2 equals 18, which is the same 18 that we've listed over here. Okay, so the answer to this question is going to be 9 times 2, the number of options for choice number 1, the number of options for digit number 2, multiply those together, 9 times 2 equals 18. In a city, bus route numbers consist of natural numbers less than 100. So natural numbers are like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That means no 0, no negative numbers, and no decimals or fractions in there. Followed by the numbers A, B, C, D, and E, and F. How many different routes are possible? So, for example, like 97B could be a bus route in this situation over here. Okay, so what we have really, we have 2 choices where we have a number. So how many natural numbers less than 100? Well, so in this case they're saying less than 100, so it could be 1 to 99. That means there's 99 options. Okay, so this is for our number. And then we have our letter. Now in this case, how many letters do we have? A, B, C, D, E, and F. That means there's 6 options. 99 times 6 equals 594. Okay. Example 4. In how many ways can 4 positions be filled among 6 men and 16 women if the first 2 vacancies are to be filled by men and the last 2 vacancies by women? All right, so in this case over here, we're making 4 choices. Okay, now it has to be man, man, woman, woman. Okay, so the first 2 vacancies by men, last 2 vacancies by women. Okay, so what do I want to think over here? How many options do I have for choice number 1? Okay, well, there are 6 men, so there's going to be 6 options right here. Okay, now option number 2, there were 6 men, but now one of them's been chosen, so that means there are only 5 men remaining. So this is going to be 6 times 5. And then for the second 2 choices, we have options for the number of women. Okay, so we have 16 women, and then 1's been chosen, so there's only 15 left. Sorry guys, I've not been calculated with me, so I'm going to have to do this off my phone here. So this answer is going to be 6 times 5 times 16 times 15, and the answer is 7,200. Okay. Example 5. Consider the word race car. This word is a palindrome because if you read the word frontwards and backwards, the result is the same. So race car spells race car backwards. Determine the amount of 5-letter palindromes. Okay, now over here, guys, like I'm not talking about, they don't have to be words because I mean that'd probably be impossible to count. But like for example, A, B, C, B, A, that would be a 5-letter palindrome over there. It's not a word. Okay, it's like abacaba, is not really a word over here. But this is a 5-letter palindrome. Okay, so you read the first 3 and the last 2 are the same as these ones over here. Okay, now how do we do this? Okay, so we're making 5 choices. First of all, we need to know that there are 26 letters in our alphabet. Okay, so what we're doing here is we're counting about percentages. Now, I guess the other thing is this a palindrome? Sure. Okay, I mean, it's A. If you read it backwards, it's the exact same thing in that order as well. Okay, so in other words, there's no restriction on what we call repeated letters. Okay, so in other words, you can repeat letters because this is technically going to be a palindrome. If you read it this way, it's A. If you read it going backwards, it's the same thing. So really, for your first letter, there are 26 different options. In your second letter, there are 26 different options. But here's where it gets a little bit different. Letters 1, 2, and 3 in this example are going to be 26 times 26 times 26. But number 4 and 5 are going to be 1 and 1. And here's why. Because suppose I place a B for my second letter. That means the fourth letter has to be B. There's no other choice. Okay, so in other words, this one has to match up with whatever this one was over here. And that means this one, A, has to match up with the first letter. So if this one was A, this one has to be A as well. So there's no restrictions over here. Right? For example, we could go like, Q, T, M, T, Q. Okay, so there's no restrictions here or here or here, but once I've placed letters 1 and 2, letter number 3 has to be the same as this one. Letter number 5 has to be the same as this one over here. So there's only one option here and one option here. Okay, so again, just going to go and do this on your calculator here. We have 26 times 26 times 26 equals 17,576. Example 6. How many odd 3-digit numbers can be made using the numbers 1, 2, 3, 4, 5 if the digits can be repeated? All right, so the question was, what are odd numbers? Odd numbers, well, in this case, 1, 3, and 5 are odd numbers, but the number 245 is odd because the last digit is odd. So in other words, it doesn't matter what the first two digits are, okay, as long as the last digit is odd. Like if I have 134, this is even because the last digit is even. Okay, all right, so in other words, if we have a 3-digit number here, and numbers can be repeated, let's do this one first. There's only 3 possibilities here, because this could be 1 or 3 or 5. Now for here, digits can be repeated. There are no restrictions on the first 2 digits, so 5 times 5 is 25, times 3 equals 75 possibilities. Okay? Example 6b, if digits cannot be repeated. So a little bit more difficult here. We're going to start by placing the last digit first. This digit has to be either 1 or 3 or 5. So there are 3 possibilities. Okay. Now, the thing that's a little bit different about here, again, we have 1, 2, 3, 4, 5. Let's suppose I used a 5 in my last spot. That would mean, since I'm not allowed to reuse the number 5, that means there's only 4 options left. So that means there would be 4 options here. Suppose I used a 2 as my first digit. That would mean I can't reuse a 2 and I can't reuse the 5. That means there's either 1, 3, or 4. So there would be 3 options for the second digit. So 4 times 3 times 3 is 36. Okay. They cannot be repeated, and the number has to be less than 200. Okay. So a little bit tricky over here. We call these guys permutations with restrictions. Okay. Now, if the number has to be less than 200, does this imply that the first digit must be 1? And here's why. It's like, well, if the number began with a 2, that would be a number in the 200s, and that means it's not less than 200, or 3, or 4, or 5. Those ones are all going to be bigger than 200. So really, there's only one possibility here. This number has to be the digit number 1. Okay. Now we're saying it still has to be an odd number over here. That means there's 2 options left, because this could be a 3 or a 5. Okay. Now, if I place 1 digit here and 1 digit here, and there were 5 originally, that means there's only 3 options left. Okay, so 1 times 3 times 2 equals 6. Okay. They cannot be repeated, and the number has to be less than 400. This question gets to be, I mean, it looks very similar to C, but unfortunately, guys, this one is actually quite a bit more complicated over here. Here's why. So let's look at our three-digit number here. First of all, it has to be odd, and it has to be less than 400. So that means less than 400 has to be 1 or 2 or 3. Okay, so we have three possibilities here. And then this number has to be 1 or 3 or 5. Okay, now the problem is, if I choose a 5 in this digit here, that means there's three options here. It could be 1 or 2 or 3. But if this number over here is a 1 or a 3, that means there's only two options over here. Okay, so the number of cases here depends on the number of cases, depends on what this choice over here is going to be. So what we need to do is we actually need to do what we call a case analysis for this. Now, okay, so case 1, I'm going to say last digit is 5. That means there's only one option for the last digit is 5. Okay, that means there's three options here now, because it has to be 1 or 2 or 3. We've placed two digits, the 3, and then either 1, 2, or 3. That means there's three digits left. We have 3 times 3 times 1. Case 2, last digit is 1 or 3. Okay, that means there's two options here. Well, if the last digit is 1 or 3, and the first digit has to be 1 or 2 or 3, that means there's only going to be two options here. Okay, and then if I place a digit here and one here, that means there's three digits left for the second digit. 3 times 3 times 1 equals 9. 2 times 3 times 2 is 12. And this answer is going to be, let's put an arrow like this, 9 plus 12 is 21. Okay? Okay. Suppose 5 friends, Andrea, Brian, Charles, Danielle, and Elizabeth, go to a movie. How many ways can the 5 friends sit if there are no restrictions? Okay, and it's just okay. So sorry guys, it's this question over here. For question number part B, they're saying the boys and the girls must alternate. Guys, these are kind of, I'm going to say, kind of traditional boy and female and male names. So Andrew will be female, Brian and Charles are boys, Danielle and Elizabeth are going to be girls. Okay, guys, this is just for the nature of this question, how this is going to have to work. So if there are no restrictions, we have here the 5 spaces where the friends could sit over here. Okay, so in other words, we're figuring out how many orders can we arrange these people. Okay, well, really, there's no restrictions. That means I could place any one of the 5 friends in spot number 1. Okay, then there's 4 friends left, so it's going to be 4, then 3, then 2, and 1. If we multiply these guys together, we get an answer of 120. Okay, the boys and the girls must alternate. So in this question over here, there are 3 girls and 2 boys. So if this is the case, I hope we can see that it has to go girl, boy, girl, boy, girl. Okay, so this is how it's going to work here. So if this is our condition over here, so we have some restrictions we need to account for here. Okay, how many spots or options do we have for spot number 1? Well, there's 3 girls. How many spots do we have for spot number 2? Well, there's 2 boys. That means this is going to be a 2. I've placed 1 girl and 1 boy, so that means there are 2 girls left and then 1 boy left, and there's 1 girl left for the last spot over there. So this question is going to be 3 times 2 times 2 times 1 times 1. 3 times 2 is 6, times 2 is 12. Okay, Charles and Danielle have to sit together. So the way we do this question over here is we're going to say, in questions where we're saying that 2 objects or 2 people or the 2 things that we're counting, whatever they are, have to be grouped together over here, we're going to treat those two objects or people as if they were one object or people. So in this case, we have Charles and Danielle, and then we have Andrea, Brian, and Elizabeth here. So really, we're only placing 4. So it'll be 4 times 3 times 2 times 1. Okay, and that would give us this over here. So far, this answer is 24. Okay, all right. There's one more thing we need to do over here. We're going to have to multiply this answer by 2. Now, the reason why we're doing that is because, like, in this case, so this would be like one possible arrangement where Charles and Danielle are sitting next to each other, okay? But we're talking about how many ways can the 5 friends sit. Well, what if I did this? If I had Charles and Danielle here, couldn't I just flip those 2 and make it Danielle and Charles, like this? So this is a different way that these 5 people could be arranged, but then Charles and Danielle are still together over here, okay? So for every one of these possibilities that we get for, in this case over here, well, I could just flip the order of Charles and Danielle, and that would give me a different arrangement altogether. Okay, guys, so I know there's a lot of questions over here so far, and it may kind of seem a bit overwhelming over here. As we go through this unit, guys, a way I can describe it is that this unit, it's common sense on steroids. Okay, so what I mean by that is, like, it's a very logical unit, and once it's explained to you, it's like, oh yeah, that makes sense. Oh yeah, that makes sense. Oh yeah, that makes sense. But like, it really does take every question to be explained to you about why it works, and then, like, it takes a lot of practice so you can recognize how this question works like that, so you can be able to kind of, identify this question correctly and do it correctly on a test. Okay, so guys, I hope this helps, and I will see you in the next part of this chapter as well.